Welcome to part 3 of the Mastering Scientific Cameras course from Tucsen. In this part, Capturing Details, we're going to be examining resolution and field of view. First of all, resolution is this question of how fine a detail can we actually measure in our image. It's one of the commonly misunderstood or at least poorly defined quantities in camera-based imaging, where in scientific imaging we mean something quite specific by it, and we're going to be drilling down into what exactly resolution is, how to optimize it, how much of it we might need in this section. And then we'll look at optical setup and mounts, looking at the different options for physically connecting a camera to our optical system. So in this section we're going to be defining resolution, and to us resolution means capturing fine details. Say you're trying to capture or resolve fine details in your subject. You're really talking about zooming right in, maybe in your image in software, and being able to tell exactly what's going on and see clearly the fine structure of whatever your imaging subject is. What gets in your way? What stops us from doing this? First of all, we could have pixelation of our image. This is where you're zooming right in and you can see the individual pixels of your camera, and you can see that the details are smaller than the pixels can represent. In this case, in this image on the left here, there's more structure that our pixels are simply too large in this case to properly represent. If we had really nicely balanced resolution, then we might see an image more like this, where everything is kind of in balance, and this is about as good as resolution can get. If we were to zoom in to this image, we would see that we are capturing the structures that are there. As far as we can tell, there's nothing beyond this that a smaller pixel would reveal, because the structures are similar to the size of our pixels. But that might not always be the case with a given optical setup and a given camera pixel size. Sometimes we might have far too many pixels than we actually need. And in this case, we're actually limited by the optics of the situation. You can see here that our pixel size is not holding us back. This image isn't pixelated, but we're still not resolving any finer details. And that might be because they're not there in the sample, but also there's the factor of our optical resolution, of how fine a detail our optical setup can show us. And we'll have a look at that in a couple of slides' time. So just to really narrow down on what we mean by resolution, there's a few different definitions that we'll come across. The most common one, in fact, because this is what it means in sort of consumer-based imaging and our iPhone and this kind of thing, that the definition of resolution in this context, what I'd call the camera resolution, this is how many pixels does the camera have. Say we have this example here of a camera that has a pixel grid of 2048 by 2048 pixels. That's 4 megapixel resolution, we would say. But that's not the definition that I'm going to be using in this course, because when we're in scientific imaging, we mean something quite literal by resolution. What can we resolve? And again, I'll define this in more rigor later on. But the key thing to know is that we have, first of all, an optical resolution of how blurred our sample is, how much are we actually getting the details of our sample delivered to the camera by the optical system. This is a really important factor. And this is defined by the type and the quality of optics used, as well as quantities like the wavelength of light. And then we have what I'd call the true camera resolution, the actual resolving power of that camera. And that is determined by the pixel size. As you can see in these two different examples, where on the left, once again, we have our pixelated image. If we had smaller pixels, we would resolve fine details. And that's our true camera resolution. But once again, there's a limit to how effective that can be. So let's have a look in greater detail at this optical or microscope resolution. The question is, how good are your optics. Say we have some perfect ground truth, represented very literally here by this image, where this is, say, the exact literal locations of fluorescent molecules, or this is some perfect image that we're looking at with a lens-based system. No matter how good our optics, everything is always going to be slightly blurred, because that's how the physics of light propagating through lenses works. We're never going to see that perfect ground truth with our camera, down to molecular perfect locations. Once this image goes through our camera lens or our microscope objective, it's going to be blurred and spread out according to the quality of those optics, according to the wavelength of light, and just generally according to what's happening optically in our system. The extent of this blurring will change greatly from one optical setup to the next, and whether our imaging subject is so small that the wavelength of light does start to come into play, but really everything will be slightly blurred when it passes through a lens-based system. But in microscopy, the wavelength of light is very frequently something that we have to take into consideration. Looking in more detail at what happens in microscopes now, in microscopes it's not just our optics, it's the wavelength of light, as I've mentioned, and we can calculate what the smallest detail we can measure is. And now we're talking about microscope resolution as being represented by a number. What is that physically smallest detail? For microscopes, calculating that is relatively simple. And the question becomes, how close can a pair of point sources of light, say there'd be individual fluorescent molecules or individual bright points, how close can they get while still being resolvable as two separate peaks? So we're defining our resolution by how close can these get while we can still tell that there's two of them. So here we have three images, three stages of point sources of light getting closer together, and at some point on this right hand side they've gotten so close that we can no longer with confidence say there are 2 points there, not one wider point of light. The limit where we have defined resolution to say at this point but no closer we can say we have resolved what's going on, we have resolved these 2 points as separate points, is what we call the Rayleigh limit, and that's our definition of the microscope resolution, called here D microscope. And the calculation for this is here on the left with this equation, where it's given by 1.22, which is the Rayleigh criterion, times the wavelength of light that we're using, lambda. It's divided by 2 times the numerical aperture of the objective lens. So on the microscope objective lenses, we have 2 quantities given, typically the magnification, and secondly the numerical aperture. And the higher the numerical aperture, the finer details we can resolve, because the smaller this D microscope would be. If we have some structure within our imaging subject that's smaller than D microscope, we won't be able to see it clearly. It'll be blurred beyond recognition. If we look at lens-based optical setups, it's a similar kind of story, but the wavelength of light is less likely to play into it, and measuring it can become slightly more complicated. Often we'll represent the resolution of lens-based setups in line pairs per millimeter, i.e. how close can 2 lines get while we can still resolve that they are 2 lines and not one wider line. And there's multiple factors that will come into play here for lenses. First of all, the F number of the lens, also which is an analog for the size of the aperture of the lens, which is equivalent to numerical aperture in microscope objectives. Factors like aberration and other artifacts that we can get within lenses that can defeat our aims of resolving fine details. And finally, the contrast with which we can image. How much clear delineation can we make between bright points and dark points? All of these things will come into play for defining whether we can confidently say we've resolved a detail or not. With lens-based systems and more complicated systems, it's often not so simple as just to say, here's an equation to tell you what you can resolve. We often have to measure this experimentally with charts and targets, such as this one here. So that's the optics side of things. What about the camera itself, this pixel size question? So with camera resolution, we slightly turn things on their head and say not how big are our pixels, but how often in space are we sampling? How close together in space are our measurements? Say we have this image delivered to our camera by our optics. If we have a grid of camera pixels capturing this image, where each yellow box is one sample, if our pixel size is smaller, then we're sampling more often. We're making more frequent measurements in space. And this is our sampling rate. And this is an important thing to understand when we're talking about resolution. But all it is, our spatial sampling is just the inverse of our pixel size, basically. In this case, we have undersampled our results. You know, if this was on the left was our image delivered to the camera, and this was the size of our pixels, then you can see on the right, we're pretty pixelated. We're not seeing much of what's going on in this case because we are undersampling. We're not sampling often enough. We're not measuring often enough to really see what's going on. So how far should we push the pixel size? As I talked about before, you can take this too small. You can take this so small that we're not actually gaining anything because we're just seeing our blurring more accurately, which doesn't actually do us any good. The question is, are we matching Nyquist? This is a concept originally from electrical engineering and signal theory. But our aim with ideal sampling, if we want to push resolution as far as we practically can get benefits from, but no further, because remember we have a trade-off here with smaller pixels being less sensitive. So what's the ideal balancing What's the ideal balancing point? This is Nyquist sampling. And the idea is that we have to make measurements, we have to sample at least twice as often as our signal demands. To show what that means in practice, say this is the signal that our microscope or our optical system would deliver to the camera. You can see that these points are close together, but they're not so close together that we can't tell them apart. We're still clearly resolving these four different objects from our optics. And then the resolution of our microscope is the distance between them. We have D microscope as marked on the image. However, if we were to just naively set our image pixel size equal to D microscope and sample that frequently, you can see with one-time sampling where the pixel size matches the microscope resolution, we're not actually resolving what's going on. You know, each of these sort of structures sort of has its own pixel, but you can't tell that there's a gap between any of it. We're not really seeing what's going on here. This image looks kind of like one bright pixel with some sort of mess around it. You can't see what's going on really at all. Nyquist sampling demands that we need to measure at least twice as often as this. So if we now double our sampling, if we halve our image pixel size, we now reach this image where we are actually finally now clearly seeing that there's two bright regions at the top separated by a darker area, and then two bright regions at the bottom separated by a darker area. We're resolving these different structures. If this represented fluorescent molecules, we would be able to tell where the fluorescent molecules are in a way that with one-time sampling, we're certainly not able to do so accurately. If we were to decrease the pixel size further and increase sampling further, we wouldn't necessarily get much benefit because we're already up to the limit of what the microscope can deliver. That's D microscope. So if we take it much further, that's not really going to help us. However, there's one significant factor that should influence us to slightly oversample compared to just straight up 2 times sampling. And that's the question of rotation and angle. Because our pixels are, of course, square. And in these 3 images that we have in front of us now, the features of the microscope, the features of the subject are perfectly lining up with the grid of our pixels. You know, we've got vertical objects separated by perfectly vertical bright and dark lines. If, however, we had a 45-degree rotation, if we're just looking at a different part of this sample, whatever it is, and it's at 45 degrees to our grid of pixels, now we're looking at the diagonal of the pixel as being our effective sampling rate. Of course, at the diagonal, we have a square root of 2 longer distance to cover between pixels, and you can see on the image on the right, now we're not so clearly seeing what's going on anymore. The 2 spots at the bottom of the image are now sort of blurred into one on the diagonal, and we no longer can truly say we've resolved these images anymore. If we increase the sampling rate to now 2.8 times sampling, so that's 2 times the square root of 2, we are now properly resolving what's going on even at 45 degrees of rotation, even as far as we can get from the most ideal conditions of things lining up perfectly with our pixel grid. So if we go to 2.8 times sampling, where our imaging pixel size is 2.8 times smaller than the resolution of our microscope, we will cover all bases. However, there is, of course, this trade-off with decreasing sensitivity with smaller pixel size. So usually there's some degree of trade-off that we do where we don't push it all the way to 2.8, but we still do go slightly further than 2 times sampling. And what we recommend is to use 2.3 times sampling, i.e. the pixel size is 2.3 times smaller than D microscope. This gives you some cover for different angles and this kind of thing, but that still allows you a significant sensitivity advantage compared to 2.8 times sampling with smaller pixels. So how do we go about using these resolution calculations and matching things up with our microscope objectives and camera pixel sizes in the real world? Let's have a look at some examples of that. So once again, we've got this formula for calculating the resolution of our microscope, the smallest detail we can resolve, where D microscope is equal to 1.22 times the wavelength of light coming into our microscope and into our camera, divided by 2 times the numerical aperture of that microscope objective. So if we have a look at some different microscope objectives and see which values they give us for these equations, we can then have a look at the Nyquist matching pixel size for that particular objective. So say you had a camera specification sheet in front of you, this would be the value that you would compare against that camera's pixel size. Starting off with a 10 times 0.3 numerical aperture objective, we can see that with this objective, our resolution is around 1.1 micrometers or 1100 nanometers at 550 nanometers of wavelength. And at 550, we're sort of in the green verging on yellow area of the spectrum. With this resolution, our ideal pixel size of a camera to match that objective and give us the ideal balance that we've talked about would be 4.9 micrometers. If we just move through some of these other objectives, what you'll notice is that the most important factor here is that numerical aperture. As the numerical aperture increases, the smallest detail we can resolve, that D microscope, decreases, so we're able to resolve finer details. But importantly, for D microscope, the magnification of that objective doesn't actually matter. What does matter or what it matters for, is the Nyquist matching pixel size. If we look at this final objective here, the 60 times 1.4 NA oil objective, we can resolve 240 nanometer details, and our required pixel size is 6.3 micrometers. But if we go up to a 100 times objective, we're still at the same numerical aperture, resolving 240 nanometers, but now our Nyquist matching pixel size is higher. So this is a good list of different objectives you might commonly come across. What type of camera would match these? If we look now at the camera resolution for a couple of example cameras, we can ask the question, do they match? And if so, how well? And if not, how badly? And we can now look at D camera, which is equal to 2.3 times the pixel size divided by the magnification. So this is our pixel size on the specification sheet, on the sensor, divided by the total magnification of the system. Basically 2.3 times the image pixel size that we defined earlier. If we have a look at two example cameras, first of all the Tucsen Diana 95 version 2, which has 11 micrometer pixels, and then the Diana 400 BSI version 2, which has 6.5 micrometer pixels. With a 10 times objective, we can see that the large pixel camera is undersampling. This will be pixelated by a fair margin, because we're comparing here 5.1 to 11. Our pixels are more than twice the size that we'd want them to. With a 6.5 micrometer Diana 400 BSI version 2, we're not so far off, within sort of 20% of our desired pixel size. Now, depending on how important resolution is for your application, that might be plenty close enough, or it might be way off. It depends on your application and how important resolving fine details is. As we look through different objectives, we can see that for many of them, the smaller pixel matches very nicely, or is just that little bit undersampled, whereas the larger pixel is way undersampled for these objectives. But as numerical apertures and magnifications start to get higher, larger pixels starts to come into its own. So with this 60 times air objective, say 0.8 numerical aperture, the 11 micrometer pixel matches it perfectly, whereas our 6.5 is oversampled, so we're throwing away sensitivity for no real advantage. Conversely, for a 60 times high numerical aperture oil objective, we have 1.4 NA, for example. Now our 6.5 micrometer pixel is a perfect match. And finally, for 100 times objective with, again, oil immersion high NA, our 11 micrometer pixel is a perfect match. So all of this is down to your application, how important it is. But it's very simple to calculate what the rough matching is between these two factors. But make sure to do it at the wavelength that you're most interested in for your imaging application, because of course all of this is different for different wavelengths. So to sum up resolution, it is of course this balancing act. With undersampling, we have this degree of pixelation, but we get this sensitivity advantage that we talked about at the start. We have bigger pixels collecting more light. So if you're challenged for sensitivity, undersampling might be highly desirable in your application. If we're matching Nyquist, that's the ideal sampling for many imaging applications to get the best detail that you can from images. And finally, oversampling is not usually desirable, but it can be required by some imaging techniques, by some advanced imaging techniques that require oversampling, but that is relatively rare. Usually oversampling is something you want to avoid. Moving on now to the subject of field of view, or imaging area of our sensor. The question here is, how much of your sample can you actually see? How much of your subject can you see? How broad a view do you get? And the field of view is a product of your pixel size, the number of pixels, and the magnification or optics that you're using. For objective-based systems like microscopes, we can fairly easily calculate the field of view. and fairly easily express it as a distance in x and y, as width and height. Say we have this field of view delivered by the microscope. This might be what you see down the eyepieces. We would have a certain portion of this field of view captured by our camera, and this is our camera's field of view. The field of view in x and y is given then by the pixel count of our camera in x and y multiplied by the pixel size divided by the magnification. It's just how many we have and how large they are in image space in each of x and y. For lens-based systems, though, field of view can instead be expressed as an angle or angle of view. And here this is how wide an area can we capture, because of course if you're closer to your imaging subject, you're going to be capturing a smaller amount of that subject than if your subject is really further away. You'll see much more of it. This is very simple and intuitive, but we can define it mathematically by the angle of view that our lens captures. And this is influenced by the size of the camera sensor up to a point, limited by the lens itself. But we have this formula here for calculating what that actual angle of view will be, based again on the pixel count and the pixel size, but here the focal length of our lens comes into play as well. But an important thing to note is that these are the maximum values that the camera can deliver, but not necessarily what you're going to get depending on your optics, your mounting system that you used between the camera and the optics, the illumination that you've got. Maybe you don't practically have illumination out to the corners of your image. So this is purely the theoretical maximum for the camera. Speaking of optical setup and mounts, we have this question of how the camera can physically connect to the rest of the optical system. And we have a number of different options here, depending on what kind of setup you have that you're connecting the camera to, and how large a field of view you need to actually support for that camera. For example, we have large sensor format cameras that might need a specialist large format mount. Otherwise, we're going to crop the field of view that the optics will deliver. We have, for example, F-mount or M42, or also custom mounting options provided by Tucsen, which can provide really large format sensors the entire uncropped field of view, 42mm or more. If we have, for example, the Diana 400 BSI version 2, this has the smallest of the common mounting options, but also the most common and versatile in microscopy, which is the C-mount. This is up to 22mm fields of view, which matches what the Diana 400 BSI version 2 requires. So we have no cropping here. On the other end of the spectrum, we have the Diana 6060 BSI, which can offer a custom mount because it's got such a large sensor that a C-mount, for example, would crop a significant portion of our image out. And here we have just a little table of different mounting options and some of the different characteristics of them. And you can see that the C-mount has the smallest maximum sensor size, but it's the most commonly used mounting option for microscopes. So, in summary, first of all, we looked at resolution, and we defined resolution as how close together can objects get and still be resolved as two objects and not one. This is our sort of true definition of resolution. Then we looked at the true camera resolution. And this is not just how many megapixels the camera has, it's represented by the pixel size of the camera and how much that limits or doesn't limit the small details that we can capture with our camera. How sort of pixelated is the image. And the true camera resolution is given by the pixel size divided by the total magnification of our system, times this Nyquist factor that we talked about, where we recommend 2.3, but it's really down to your application, how important resolution is for your application versus, say, the sensitivity of having larger camera pixels. We also looked at optical resolution, and for microscopes this depends on the wavelength of light that we're working with and the numerical aperture of the objective. For lens-based imaging setups, this is slightly more complicated. And finally, we looked at this idea of matching up the resolution of our microscope or our optics to the resolution of our camera. And in an ideal case for most applications, resolution is best when both of these match. If we have larger pixels than this would ask for, then we undersample and we have sort of pixelation. But we do get a sensitivity advantage from this. Smaller pixels than our Nyquist matching would ask for oversample, and there's a sensitivity cost for this, which is rarely beneficial. Next, we looked briefly at field of view for camera systems, and we can split this roughly into camera field of view, where the sensor size is the very important factor. But we also need to consider the magnification, and this leads us on to the optical field of view, where the magnification used defines the maximum field of view that a camera can give, but the optics and the mounts may also have limits, whether that's through how broad an area we can illuminate with our microscope, or whether we might have vignetting at the edge of a lens, or whatever it might be. There might be limits to this maximum field of view that you must consider for your application. Finally, for our examples and applications for part 3, we're going to be considering where resolution is really important, in what applications is resolution important, and where is field of view really limited in the real world. Next, to have a look at some examples for resolution. The question is, how much resolution does your application need? I talked a lot in the presentation about how to really fine-tune and get the absolute best resolving power for the finest details. Not every application actually needs this. Some need to go even further and go beyond the optical resolution that's typically possible, and then we have super resolution methods, but usually we're going to be somewhere in between, and the question is, how much resolution do you need? Most applications will benefit from maximizing imaging resolution, but not all. Because resolution, remember, is a trade-off with sensitivity, and in fact as well with field of view. If we zoom in further on our image, we can imagine that we're going to see less of it. So how do different applications typically benefit from maximizing resolution if we plot them from sort of more benefit to less benefit? With the more benefit side, we have things like imaging very small objects like bacteria and yeast. In this case, we really need high resolution optics and high resolution cameras matched to those optics to really see what's going on. We don't really have much choice. On the other end of the spectrum, we have things like electrophysiology and neuroscience, and cameras for patch clamping in this kind of application where you don't really need to see the fine details of what's going on. You just need to see very clearly what's going on, and that's it. Somewhere in the middle we have things like documentation imaging, where it's very important that the image looks good and it's clear and it's publishable quality. And somewhere in the middle again, we have things like high content imaging, where there's something of an industry standard of how fine our resolution wants to be, but it's not at the extremes on either end. Next, we have examples for field of view and optics. And the question is, what limits your field of view? If you're using a microscope, most microscopes offer around 19 millimeters of even illumination and 19 millimeters of flat focus. Sometimes now, though, that's 25 millimeters for some microscopes, but usually there is some form of limit on the microscope side for how big the field of view can get. So it doesn't make a huge amount of sense for cameras to offer significantly more field of view than the microscope. But some custom optical bench setups can offer larger field of views than standard off-the-shelf microscopes. We also need to bear in mind what different mounts and optics options do we need. And as I mentioned before, most microscopes do use C-mount to mount the cameras, which, as we can see, with the 22mm maximum throughput of a C-mount, that matches what most microscopes are capable of delivering. You can in fact get lenses inside the C-mount component to change the overall magnification of the system sometimes, which can help match things up. But more microscopes are moving to f-mount to offer larger field of views up to that 25mm and sometimes a bit beyond. In physics and astronomy and many other applications, though, we'll often use lens-based setups, and here f-mount, t-mount or custom mounting options are quite common.